In our previous episodes, we walked through the entire process of a CE project, from start to finish. Today, we're going to scale things up. We'll explore how to expand this from a solo endeavor into a large-scale collaborative effort. This is, I believe, one of the most critical future directions for the CE approach. Our existing CE projects, like the case study we've discussed, already represent a massive leap in scale over traditional methods. They yield hundreds of times more data, allowing us to study multiple mechanisms simultaneously rather than in isolation. But let's be clear, these projects still have deliberately limited scope. Our case study focused only on color memory for 4 items. It intentionally excluded other critical factors, such as the number of items, their timing, and other features like object identity. That's why I call it quasi-comprehensive exploration. It's a major step, but not the final destination. So, the obvious next step is a truly comprehensive investigation, one that incorporates all these dimensions. But this ambition requires large-scale collaboration for 2 key reasons. First, the scale is unprecedented. We're aiming for about 330,000 participant hours, 10 times our previous case study. This simply isn't feasible for a single lab. It demands shared resources across many teams. Second, and more importantly, this collaboration aims to create something revolutionary, a standardized benchmark dataset for visual working memory, a psychological image net. But a benchmark is useless if nobody uses it. That's why broad participation is critical. It ensures field-wide awareness and builds the consensus necessary for adoption. Only then can it become a shared, lasting foundation that researchers will actually use to drive theoretical progress. Now, large-scale collaboration is famously difficult. The Cogitate project in consciousness research shows why. Despite involving leading theorists, it made limited progress. Critics noted that it only tested idiosyncratic predictions and handpicked auxiliary components already known to be true and avoided core theoretical claims. This difficulty is predictable. As we've discussed in Episode 8, high-dimensional theory-driven design is inherently challenging. In collaborative settings, this challenge is magnified by self-serving biases. Researchers naturally avoid tests that might threaten their theoretical positions. Let me illustrate this bias. Imagine 2 theories, A and B, and a range of possible experiments. Supporters of theory A will argue against tests that might challenge their view. Supporters of theory B will do the same. The result? The group converges on a safe set of experiments, ones that don't threaten anyone. This process systematically filters out the most critical tests, leaving only well-known, uncontroversial findings. The final design may be agreeable, but it won't drive theoretical progress. Self-serving bias, like aversion to complexity, is an inherent human limitation. We cannot simply choose to turn it off, no matter how much we might want to. That's why researchers who take on the challenge of collaboration should be praised for their courage, not criticized for struggling against fundamental cognitive constraints. This brings us to a crucial insight. It would be far better to develop a framework that works with our cognitive tendencies rather than one that forces us to constantly fight against them. What we need is a method that makes collaboration inherently easier, from start to finish. A typical adversarial collaboration has 5 steps. First, agree on theories to test. Second, agree on stimuli to use. Third, agree how theories map to stimuli. Fourth, collect data. Fifth, agree how to interpret the data. Steps 2 and 4 are straightforward. However, steps 1, 3, and 5 are significantly more challenging. These steps require theoretical consensus, precisely where deep disagreements and cognitive biases emerge. The collaborative CE approach is dramatically simpler. We only need 2 straightforward steps: to agree on stimuli to use and to collect data. We skip all the hard parts. Because it uses a stimulus-driven design, collaborators don't need to agree on theoretical interpretations before collecting data. This makes the first and third steps completely unnecessary. This theory-neutral foundation minimizes conflict. For example, would anyone feel threatened by 10,000 random color patterns? Probably not. Furthermore, following the ImageNet model, the project concludes by releasing an open benchmark dataset, making the 5th step unnecessary as well. There's no need for consensus on interpretation, since researchers can independently test their models against this shared standard. This eliminates the biggest hurdle of traditional collaboration. To sum it up, the collaborative CE approach makes teamwork easier because we don't need to agree on theories before data collection, and we don't need to agree on what the data means after data collection. The only thing we need to agree on is the general phenomenon we want to study. Guided by this design, a large-scale collaborative CE project on visual working memory is already underway, co-led by Klaus Oberauer and myself. While this project focuses on working memory, the collaborative CE approach is not domain-specific. It can be applied to any area of psychology that needs a stronger foundational data set. If this project succeeds, and I believe it will, it could do more than just answer old questions. It could establish standardized benchmarking as a regular practice in psychology, potentially catalyzing a genuine paradigm shift. I'll discuss this exciting possibility in our next episode. See you then.